The next topic that we will cover is this knowledge distillation, which is also known as teacher and student architectures. So these architectures are useful for a number of tasks. Here we have some of them. So for instance, model compression. So the teacher would be a large model that is computationally more expensive, and the distillation transfers this knowledge to a smaller, more efficient student model that could work with fewer resources. They also help for generalization, because very often the input labels have noise, and then the teachers provide soft labels with fewer noise, less amount of noise, and they provide richer interclass relationships that the students can use to learn in a smoother, more generalizable representations. Then we also can do knowledge transfer. So this somehow highlights the previous two ideas. Robustness to noisy data we have also commented. Then simplified ensembles. So the students can distill the knowledge from multiple teachers. So one student could achieve near ensemble accuracy with reduced complexity at the level of inference. They will save energy because they normally are smaller networks, and they are more lightweight, so it is easier to deploy in any other kind of devices. So there are multiple ways to do this knowledge transfer. So let's say that we have an input, some input vectors that have to predict some, let's say here in this example, hard labels y. So this teacher would produce some soft labels. So these soft labels are achieved with a high temperature. So the high temperature makes this is the softmax expression with temperature. So the having a high temperature makes all the predicted probabilities or the probabilities of having a particular label to be more uniform, to be less peaked. So when you have very low temperature, normally one of the probabilities dominates all the others, but with high temperatures they are more smoother. So now the student has to, with the same temperature, it has to predict the same soft labels as the teacher, but also it has another loss that is, so this loss is called the distillation loss, so trying to mimic the behavior of the teacher, but then it has also a student loss that is trying to make this hard prediction with a smaller temperature so that it goes to the ground truth. Another way to make this knowledge transfer is what is called this response-based knowledge distillation. So the student tries just to reproduce the teacher's output. So we have just one distillation loss, and this can be done at the output, so at the level of logits, as we saw it here. So the logits are these softmax predictions, or they can be at the level of layers. So this feature-based knowledge distillation. So the student tries to reproduce the teacher's internal layers. So here we would have it. And another possibility is this relation-based knowledge distillation. So the student reproduces the distances and angles, so the relationship between points of the embedded points in the teacher's latent space. So the teacher has some latent space, and then the student has to reproduce the same kind of latent representations, but with a smaller network. And again, this is a distillation loss. This distillation can be performed offline, so the teacher is optimized first, and then the student learns on the teacher. Can be done simultaneously, so the teacher and the student learn both at the same time, or it can be self-distillation. So there are several. So the teacher and the student is the same network, and somehow there is part of the network that acts as the teacher of the other part of the network. This can be at the level of layers, so the deeper layers of the teacher, so the deeper layers of the model, so the later layers are somehow distilled to the earlier layers. So the earlier layers are the student. And then temporal self-distillation. The model's prediction from earlier epochs guide its learning in later epochs. So the first epochs act as the teacher of the later epochs, or it can be prediction refinement. So the models of logics guide its learning alongside the true labels. So here we have a beautiful example of this self-distillation, where we have some input vectors. So these input vectors have to produce an output, and then these layers here would be the student. This would be the student model. This would be the self-distillation model, and then there is a loss between these two layers. So this act as the teacher, and this part act as the student, and it has to produce an output. And later we can get rid of these green blocks and just run the blue blocks, the student blocks, to produce an output which is cheaper. Here we have an architecture doing that. So given an image, you have to predict what is the label associated to that image, and that can be done through these rest blocks. So this would be the student, and then this would be some self-distillation modules that try to guide the learning of these student modules. So this would be it for the self-distillation. See you in the next lecture.